Okay, hey, so we're making a video about upper and lower bounds here. First, we're going to review the idea of rounding. So rounding to the nearest tenth means this is the 10th position. This is the 100ths position right there. And we're going to need to round to the nearest tenth. And effectively, we want to make our number 3.5, right? Now, that's not quite right because this number is a 6. So because that number is bigger than 5, or 5 or larger, we have to round up, so it's going to be a 3.6, okay? And so you're going to want to round to the nearest tenth like that. Same thing here. These 5-0 means we're going to round this 7 up to an 8, okay? So rounding to the nearest tenth. Something that you would round to the nearest tenth, let's say I ended up putting 11.225, for example. This would be 11.2, because this number 2 is between 0 and 4, so 0, 1, 2, 3, and 4. So therefore, you keep this number as is. All right? It's a bit of a review on rounding. I think it's a pretty common thing to know. So why do we want to review that? Because now what we're doing is we're talking about determining the upper and lower bound for particular measurements. So this measurement is accurate to 1 decimal place, meaning this is the 1 decimal place that we want, that we were rounded to. So my question is what numbers could have rounded to 2.7, right? If you think of this on a number line, 2.7 is here, and 2.6 is there, and 2.8 is there. And effectively, if I was to sort of start right here and end right there, oh, those are big. Let me erase those. Let me make that a bit less thick. There. Back to the drawing board. Okay, let's do that now. If I were to start right here at, for example, 2.65, and then go any number in this area would have been rounded to 2.7. Then up here at 2.75, which is right there, all of these numbers also would have been rounded to 2.7. So basically the range of values that would round to 2.7 are anywhere between 2.65, this is known as the lower bound, and this is known as the upper bound, okay? And that's kind of the idea. Now, on the upper bound, you're going to want to change this to a 4-9 repeating, because technically speaking, a 2.75 would round to a 2.8. So for your upper bound, you want to always write at the most a 4-9 there. So this one over here is accurate to the 100th place. And so it's 33.37. And so this is the 100th place. So if I again think of this on a number line, 33.37 is on the number line. Now I'm zoomed way in to this number line. Over here is 33.36. Over here is 33.38. And again, I'll switch to a different color. From here until here, the midway points, these guys would round to a 33.37. So the lower bound is here, where the upper bound is here. Okay, So my lower bound is 33.365, halfway between 3.6 and 3.7, 0.36 and 0.37. Up here, my upper bound is 33.375, but I'm not going to write a 7.5, I'm going to write a 7.49 repeating, because if it were a 7.5, it would round up to a 33.38. Okay, so that's how we do our upper bounds and lower bounds. Now, these questions, a series of several questions, these next questions here, says a new electric car has traveled 321 meters in 20 seconds. The meters is correct to the nearest meter. And the speed appears to be correct to the second, to the nearest second. So what I want to do here is I want to find what numbers could have been the distance. So 321, 320, and 322. So it would have been any one of these values in here could have been the actual distance that it traveled. Okay. Then for this is the distance. For the time, right, we've got 20 seconds, 19 seconds, and 21 seconds here. So my time could have been anywhere between here and here. So again, my lowest distance it could have been is 321.5. My highest, sorry, I said that wrong, 320.5, which is here. My highest would have been 321.5. Time, my lowest time would have been 19.5. My highest time would have been 20.5. Now again, I'd use 0.49 repeating for both of these ones. Now the question is determine the fastest it could be. So in order to go fast, I need a big distance. Remember, speed is distance over time, right? So I need a big distance in a small time. That's how I go fast, right? So my biggest possible distance was 321.5, which is this. So 321.49 repeating over my smallest time is my shortest amount of time that I would have been able to do it in would have been 19.5 seconds. So 19.5 seconds. Okay, and this is my fastest possible velocity. So I just calculate that on our handy trusty calculator. Oh, I mean calculator. Where am I going to get that? There it is. So it's 21.4999. You could really just use a 0.5 here, but just divided by 19.5, giving me 16.48, right? So 16.48 meters per second. All right. Now, my slowest possible time, my slowest possible velocity would have been distance over time again, which is velocity. But in order to do a slow velocity, I need a small distance over a big time. So I need to go not very far, small distance, and needs to take me a long time. So my smallest possible distance was 320.5 meters, and my biggest possible time, the longest it could have possibly taken me, would have been 20.5 or 49 repeating seconds. I should write a 49 repeating here. But I'll do that with my handy calculator. And there we are. Clear it all out. And so we're going to do, 320.5 divided by 20.5. We're getting, my slowest possible time would have been 15.63 meters per second, or 15.63 meters per second. Okay, there's quite a bit of a discrepancy, almost a full meter per second between those two things, right? So a lot of people would say, well, they went 321 exactly, and they did it in 20 seconds, and so they would just say, my velocity is 321 divided by 20 seconds, so it's 16.05 meters per second. But that's sort of the mid-range of the possible, of what it should be. But be aware that there is, every time you take a measurement, there is some sort of inaccuracy built into it. If you're combining measurements, the inaccuracy is sort of compounded by the fact that both of these numbers are inaccurate. Okay? So that's kind of the thing you want to keep in mind there. So let's do this again now. If the following measurements are accurate to the nearest centimeter, what's the largest and the smallest that the cone could be? So again, or not again, but for the first time, let's remember that the volume of a cone is 1/3 pi r squared h, where r is 2 and h is 6 in this case. But remember, these are each accurate to the nearest centimeter, meaning this 6 could actually be 6.5, or it could be 5.5, because remember, we rounded it. Now, of course, hold on a second, not 6.5, it should be 6.49 repeating is the biggest that it could be. All right, 6.49. That's the biggest the height could be. The smallest it could be is 5.5. My radius could be 2.49 repeating as the biggest, and it could be 1.5 at the smallest, because remember, these are numbers that have been rounded to the nearest centimeter. So if I measure 1.5 centimeters, I would round it to 2. If I would have measured 2.49 or less, I would have also rounded that to 2. So now the question is, what's the largest that the cone could be? So for volume, I want a large radius and a large height to give me a large volume. Volume, large, I'll write here. Large. It's going to give me a large, so 1/3 pi r. So I need the largest r, which is 2.49. Whoops, I got to erase that. 2.49 squared times the largest height is 4.49 repeating. And this is going to be my largest volume. My smallest volume, possible volume, is going to be 1/3 pi 1.5 squared times 5.5 squared. This is supposed to be a 6, by the way. 6. I don't know why I wrote a 4 there. Let me fix that up. Now, I'm not going to calculate these. Well, I'll calculate the first one, I guess. Do I have a pi button? I sure do. Cool. So I could do 1/3, which is, I'll just divide everything by 3 at the end to get a 1/3. So it's pi times 2.49 but I'll just write a 5 because 49 repeating, 99999 is effectively 0.25. Then I got to square it, but since I've got a funny calculator, if I hit the square button now, I think it'll give me a funny answer. So I'm just going to multiply it by another 2.5, so that's squared. And then I'll multiply it by a 6.5. And then I'll take the whole thing and I'll divide it by 3, giving me a 42.54 is my largest volume. Cubic centimeters. And then the same thing for here. Might as well just go for the whole thing. Pi times 1.5 times, 1.5 times 5.5 equals 38.3. Take the whole thing and divide by 3. 12.95. 12.95 centimeters cubed. Wow, that's a pretty intense discrepancy. So based on the fact that these measurements are, they have a full range of a centimeter potential error in this measurement and a full centimeter in this one as well, gives me the fact that my largest possible volume is 42 and my smallest possible volume is 13. It's a huge thing there. Oh, I don't know why I squared my 5.5. That wasn't supposed to be squared. Anyway, so that's that. Okay. It says a rectangle with an area of 35 centimeters squared, correct to the nearest square meter, has a width of 10 centimeters, correct to 1 centimeter. Determine the largest and the smallest that its length can be, right? So remember that an area, I think I'm on a race. The area of a rectangle is base times height, right? Oh, what am I doing here? Base times height. We'll go ahead and draw ourselves a little bit of a rectangle. Here's my base, here's my height. And we know that the area is 35.7. This is correct to the nearest square meter. It has a width of 10 centimeters, okay? Correct to 1 centimeter. Determine the largest and the smallest that its length can be, okay? Oh, I guess I'm going to do length. Length and width. Base times height. Sometimes they call these length and width, okay? So, and I'll use the same thing over here, length and width. Length times width. Now, question is, what is my area? I want to figure out what's the largest and the smallest that the length can be. So I'm going to solve for length. Length is width, excuse me, is area divided by width. If I just do some algebra and divide this width over, I get area over width is length. So area over width is length. Now, in order to get a big length, I need a big area divided by a small width. Let me do it like this. This is very similar to the question about the velocity with small. In order to get a small length, I need a small area divided by a big width. Now, think about this. In order to make this side big, the numerator of the fraction needs to be big. And then again, if the smaller the denominator is, then the bigger a fraction is. Now down here, if I have a big denominator, the overall fraction becomes small. Remember, this overall fraction, area divided by width, is equal to the length. Okay? So now that that's being said, I'm going to want to figure out my area. Remember, it's accurate to the nearest 35. Or sorry, to the nearest centimeter. So here's 35. Here's 34. And here's 36, meaning it's anywhere between these two values from here to here. So the small area, the smallest the area could be, is 34.5. So small area, I'm going to put that right there, 34.5. The biggest that the area could be is 35.5. So the biggest the area could be is 35.5, or 49 repeating. The smallest that the width could be is 10 centimeters is what it's measured at. But it could have been 9.5, or it could have been actually 10.49 repeating. So I'm going to take my small width and stick it there, so 9.5. And I'm going to take my big width and I'm going to stick it there, 10.49 repeating. And this is the largest that the length could be up here, and this is the smallest that the length could be. So let's do this. 35.49 repeating. I'm just going to do 35.49 repeating is, I'm just going to write a 5 divided by 9.5. I get 3.736, right? 3.736. This would have been centimeters. And over here, it's 34.5 divided by 10.49 repeating. 34.5 divided by 10.49 repeating, or 10.5. So the smallest the width could have been is 3.285. I guess we'll just write 3.285 centimeters. All right. So that's kind of the idea here. Again, what we're trying to do here is take into consideration that each one of these measurements, the area and the width, have a bit of potential error in them. Okay? And so, therefore, the biggest length that the thing could have been, that would have been in the case that it had a big area and a very small width. It could be anywhere in between these two. The actual length of the rectangle could be anywhere from 3.28 to 3.736. Okay? So that's upper and lower bounds. You'll see some practice questions there. I'll also look at the next one is conversion graphs.